So next up, we're going to look at got another theorem. This is Fermat's theorem on local extrema. And remember, AP test, they may say, use the word relative, so it may be something about this on relative extrema. So we say if f of c is a local min or max, then c is a critical point of f of x. So this basically says anytime I find a local min or max, then I find a critical point. There'll be a corresponding critical point for that, which kind of makes sense, because if we had a graph that's doing this sort of deal, we'd have a local minimum here and a local maximum there. The slope of the tangent line at the local max and the local min, the slope of those tangent lines would be 0. So horizontal tangent line have slope 0. If you remember, the first derivative tells us the slope of tangent lines. So if the tangent line's horizontal, that would mean that f prime of x is 0 there. So that would mean that if the horizontal, your slope of tangent lines are horizontal, then the first derivative is going to be 0. If you remember, anywhere the first derivative 0 is a critical point. So that's basically how this works. So anytime you find a local max or min, then you also found a critical point of your function as well. So that's a nice little thing. And then we're going to get another theorem, and then we're going to spend a while. The rest of the examples will be kind of focused on this last theorem. So this last theorem here says this is extreme values on closed intervals. This one here is this turns up usually on the AP test as one of the part of the free response, or sometimes in the multiple choice. They'll ask you to kind of apply this idea. So we say assume that f of x is continuous on interval a to b. So we'll say on a closed interval a to b. And let f of c be the minimum or maximum value on that interval. On that interval a to b. Then C is either a critical point or one of the endpoints either A or B. So what this theorem says is if you want to find the biggest y value or the smallest y value of a continuous function on an interval, check your endpoints, check your critical points, and it's going to be one of those. So we kind of, what we have here is rather than having to check every single y value from all the x's in the interval, so there's infinitely many x's in the interval, Instead of having to look at every single y value and figure out who's the largest, who's the smallest, we now have kind of two things to check. Check the y values of the endpoints, check the y values of the critical points. Whoever has the largest y value of the endpoints and critical points is the max, and whoever has the smallest y value of the endpoints and critical points is the minimum. So we'll do a quick example with that, and then we'll look at another couple examples over this stuff. So this will be example 3. We want to find the extrema of f of x equals 2x cubed minus 15x squared plus 24x plus 7 on the interval 0 to 6. Okay. So we're going to start out, we're going to make a table, and we say, well, okay, in our table here, we're going to have the x values here, and these will be the y values that are generated from those x values. I know 0 is an endpoint. It's the beginning endpoint of my interval, and I know 6 is the ending endpoint of my interval. So I know I need to check those numbers, because those numbers are endpoints. So I'll put x down for them, and then I'm going to need to throw my critical points in for my list as well. And then I figure out what's the y value for the endpoints and the critical points. And the smallest one's the minimum, the biggest one's the maximum, and that's basically it. So to get my critical points, I need to get my first derivative and look and see what's going to happen with it. So I get f prime of x, that will be 6x squared, that'll be minus 30x plus 24. Again, this is a parabola. It's ax squared plus bx plus c. So there's not going to be any undefineds caused by this. So I'm just going to see, where is this equal to 0? So when I find my critical points, there is no x values that create, the first derivative does not exist. So I don't worry about those type of critical points. I'm just going to focus on the critical points that make the first derivative equal to 0. So I'll factor a 6 out. That'll leave me that. This will factor as x minus 1, x minus 4. So I get x equals 1 and x equals 4 on my critical points. Now, one thing you want to check is make sure that those critical points are within your interval. If, like, this critical point here was like 54 or something, it would be outside of 0 to 6, so we wouldn't check it. So you only check numbers in between 0 and 6. Or inside whatever your interval is. And our interval is 0 to 6. So here, 1 and 4 are both within 0 to 6, so they are both numbers I need to check. So I got to check what is f of 0, what is f of 6, what is f of 1, and what is f of 4. And make sure when you're finding these y values, make sure you go back and you use the original function. You're going to use the original function out here. You're not going to use the derivative to find the y values. You want the y values of the original function. So to help me out, I'm going to type that into my calculator. We could do it without a calculator, but just to speed stuff up, I'm going to type it in my calculator and see what y values I get back. And we'll go from there. So if I get 0, 0 gives me back 7. If I input 6, 6 gives me back 43. Okay, if I input 1, 1 gives me a y value back of 18. And if I input 4, that gives me a y value back of negative 9. So based on this, 43, f of 6, which is 43, that's my absolute maximum. And f of 4, which gave me back negative 9, that's the smallest y value I get back from my endpoints from my critical points. So that's my absolute minimum. So again, by the theorem, if I'm checking for the biggest or smallest values over an interval of a continuous function, I check the endpoints. I check all critical points that are within the interval. And the biggest y value is the maximum. The smallest y value is the minimum. So we'll do a couple more of those examples, and then we'll move on to something called Rolle's theorem. So next example. They say find the max of the function f of x equals 1 minus, open parenthesis, x minus 1 to the 2/3. And they tell us the interval we're looking at is -1 up to 2. So this time we're only interested in the maximum value. So, okay, let's build our table. We're going to say for x's and y's, we know we're going to need -1 and 2 because those are endpoints. So I got to check my endpoints. Then I got to check my critical points. So let me take the first derivative of this and see what our function looks like. And then we'll see if we can get the function equal to 0 or if we can get it undefined. The previous ones we looked at were parabolas, so they didn't have a part where the first derivative was undefined because the first derivative was just a parabola. But this one has a different form, so we'll see. Derivative of 1, 1's a constant, so it drops. This rest of this part here is going to require the chain rule. So we have a negative, the 2/3 comes down, leave the inner part alone. We got the 2/3 in the power, we're going to subtract 3/3 from it, so 2/3 minus 3/3 is -1/3, and then I got to multiply by the derivative of x minus 1, which is 1. So if I rewrite this a little bit cleaner, I have -2 over 3 times the cube root of x minus 1. Okay, so that is not a parabola. This has division in it, so it might be possible to get the first derivative undefined. So let's check if the first derivative can equal 0. We'll check that. Is that something that can cause a solution? So I'll say 0 equals my first derivative. I'm going to multiply the bottom across. Multiplies to 0. So we get basically 0 equals -2. So there is no x value that makes the function 0. So our critical points, if we have any, they don't come from where the first derivative is 0. Let's see if we can get the first derivative to not exist. Well, if I put x equals 1 in, that will cause division by 0, which will cause the first derivative to not exist. So x equals 1 is a critical point that's caused from the does not exist. So 1 is between -1 and 2, so we do need to check it. And what I'm going to do is go up here to my function. I'm going to type my function in, and then I'm going to check what y values does my function return for each of those x values. Okay, so we want basically what's f of -1, what's f of 2, and what's f of +1. So f of -1 is -0.5874. F of 2 is 0. F of 1 is 1. It asked us to find the maximum of that. So the maximum value is obtained right here. This will be the maximum, absolute maximum of that expression. Because we check the endpoints, we check the critical point, and by our theorem, that's the theorem says if you're continuous and you're a minimum or a maximum value on the interval, then you're either at a critical point or an endpoint. So we got our critical points, we got our endpoints and our critical point. We checked them, so the largest y value returned was our maximum. So our maximum value was 1 in that case. Okay, next example. This is example 5. We want to find the extreme values, which is another way of asking us to find the max and min, of the function f of x equals x squared minus 8 natural log of x on the interval 1 up to 4. Okay, so we're going to build our table, say here's our x's, here's our y's. We're going to need to check 1 and 4 because those are our endpoints. And now let's take the first derivative so we can see where is it 0, where is it undefined. First derivative is 2x minus 8 times derivative of natural log is 1 over x. So we basically got f prime of x is 2x minus 8 over x. So we're going to see where is f prime of x equal to 0. So we'll say 0 equals 2x minus 8 over x. I'll scoot the 8 over x across the equals. Multiply the x back across. Divide the 2 on over. Take plus minus square root. And we get plus minus square root of 2. Sorry, square root of 4 is 2, so plus minus 2 is x. So two of our critical points, one's at positive 2, one's at negative 2. Now let's check any x's that make f prime of x undefined. Or does not exist, I guess. Well, if I look in this form and I look at the x down here, if I let x equal 0, that will cause division by 0. So x equals 0 is another critical point I need to check. So I have 3 critical points, 2, negative 2, and 0. Let me check what numbers I'm looking at. I'm looking from 1 up to 4. So if I'm only interested in numbers 1 up to 4, negative 2 is outside of that range. So it's not from 1 up to 4. Negative 2 is outside of that range. So I'm not going to check it. 2's in the range, so 2 is good. We got to check 2. But 0 is also outside of the range. So 0, we're going to throw it out and say it's outside of the range 1 up to 4. So the only third number I really need to focus on for this one is 2. So 1 and 4 were endpoints. 2 was critical point. And the other 2 critical points, they weren't in between 1 and 4. They were outside of that region, so we don't check them because they're not within the region that we want to figure out what the y values are maximum or minimum. So I'm going to type in my function, and we're going to see what are the y values we get back from that. So we get x squared minus 8. Is that natural log of x? Okay. So when I put 1 in, I get back 1. If I put 4 in, I get back 4.9096. If I input 2, I get back negative 1.545. So 4.9096, that's our absolute maximum. It's the largest y value generated. And this negative one here is the smallest, so that's our absolute minimum. Okay. So we're going to stop on those examples there, and we'll pick up the last little bit here in a second.